Welcome to the School of Life. Life is hard, but you have got to be harder. I am Mrs. Collins, your life coach. Let's get started. Today's topic will be Unit 1, Lesson 3, Normal Distribution. We'll start off by talking about how data can be distributed in different ways. Distributed simply meaning spread out in different ways. In order to get a good understanding about the different ways that data can be spread out, we're going to look at several examples. And by the end, hopefully, you understand that data can be distributed in different ways. One of these ways will be normal distribution. And that normal distribution is what we'll take a deeper look at. But starting off, we can have data that is skewed left, which simply means that the majority of our data is on the right and the smaller part is on the left. So it's skewed left. There's like a tail on the left side. We can have data that is skewed right, where the majority of our data piles up on the left side, but the tail of our data is on the right. And then we can have something that's called no skew at all. And we'll talk about examples of when we have data that is skewed left, skewed right, as well as no skew. The last one that we'll talk about is normal distribution. Notice how it's evenly distributed across this particular curve. We'll talk about that too. So first, let's look at an example of skewed left. All right, when we have data that is skewed left, once again, we have a long tail that is on the left-hand side of our curve. There's some key features that you can pull out of these curves. And that, for anything that is skewed left, is, first off, that your mean, median, and mode are not equal to each other. Instead, the mean is to the left of the median is in the middle, and then we have the mode on the right-hand side. This would be something that's considered skewed left. Now you may think, well, what real-life example can show us something that's skewed left? Well, let's say this. Let's say that your chemistry teacher decides to give you a test. This test so happens to be a very easy test. Like very easy test. Well, if you think about all of the test scores, and this is an easy test, then the majority of the people within this particular class, or if it's like a sophomore, junior level class that's taking chemistry, the majority of people would have scored in those higher ranges of scores, like 80s, 90s, and 100s. Okay, and then there will be very few people on this easy test who scored a 0, 10, 20, 30, 40 on this particular test. So an easy test that has been given, the results, the data collected by the teacher, those scores will show that majority of the people, once again, scored in those higher ranges. Again, 80s on the test, or 90 on the test, 100s on the test. So you would see something similar to this, like a bar graph, histograph. It looks very similar to this. You have a lot of people scoring in those higher ranges than those who are scoring like the zeros or the 10 or 20, the 30s, and so on and so forth. Very small amount of people within that particular class or that particular course who are scoring in those lower ranges. So that would be considered skewed left. All right, so let's look at skewed right. So going with the same theme, those tests, tests. Hope you don't have a test this week, but if you do, I hope that you do well. Looking at difficult tests. Most students, if a teacher was to give a difficult test, when that teacher collects the results from that difficult test, very, very hard test. Let's say that this was a math test. Okay, if it was a really, really difficult test, then we'd have scores that range. Many people would have scored a score that's lower in number than those higher scores. So you'd have a lot of 10s and 20s on the test and 30s on the test, or 40s. And then there would be very few students who performed really well and got those 90s or 100s. Okay, so then this is something that we would call skewed right. In this case, the higher scores would have only been achieved by a very few people within this population, within that data set, or data set being the teacher's group of students. Very few people would have scored a really great score on that test, and the majority of people would have scored really poorly on that test. And this is if, again, the teacher gave a really difficult test. So that's a skewed right example. All right, no skew at all. The other day, we looked at the sample heights of 11th grade students. This is simply, I believe, 13 students who are in the 11th grade within Ms. Collins's class and their heights. First off, note that this data does not represent every single 11th grader across even the United States, not even across JTHS, not even within Central. This is simply a sample size. It's not the entire population of 11th graders, just 13 students. So with just these 13 students' data, we can see that, well, there's a couple of students who are between, they're 4 feet 5 inches and 4 feet 9. There are a couple of students who are 5'3", 5'4", 5'7", 6 foot. But then in between these taller heights, we also have like just one student who is 5'5", or one student who is 5'9", and one student who is 6'1". So in this particular case, we don't see a distinct pattern. Kind of goes up, it goes down, it goes up, it goes down, and so on and so forth. So this one we would call no skew. But I'd like you to note that if we were to gain more and more data of more students across the 11th grade, or more students across JTHS's 11th graders, or if we widen that, the 11th graders in the city of Joliet, or the 11th graders in the state of Illinois, or the 11th graders in the Midwestern United States, or even the 11th graders across the entire United States. The more and more data that we collect, we will start to actually see that the sample heights are actually normally distributed. Okay, so they're actually spread out normally. But in this data set, because it was only such a small amount of the population, just a sample size, you'll notice that there's no skew here. There's no distinct pattern that we can see. Okay, but let's take a look at what's classified as normal distribution. Normal distribution is where we have no bias, left or right, and we have what is called a normal distribution. With our data, we're able to see exactly where our mean would fall, our median would fall, as well as our range. And it so happens that that mean, the average, the median, the middle number, as well as the mode will all be located in the exact same place, at the very tip of your bell curve, or at the very tip of your normally distributed curve. So here would be our mean, our median, and our mode. So, well, Ms. Collins, put that into an example. What does that mean for real life? Here we go. Back to our height example. Height is something that would be represented in a normal distribution curve or situation. So, if you think about heights, if we were to gather data of heights over a wide spectrum of people, And let's just keep this one pretty simple. Let's say JTHS, so both the Central and the West Campus. If we were to gather the heights of all of the students within the Central and the West Campus, we would see a normal distribution. Okay. Keep in mind that the students within Central and West are between the grades of 9th and 12th. So there would be very few students who are very, very short. There will be the majority of our students who are around the same size. So they're considered average height. Ooh, what's another word for average? Mean. Majority of our students are average height. Oh wait, the word majority, meaning most often. There's where the mode is. Okay, and then also if you think about it, the median, the middle heights of the data set is also right in the middle of this curve. So whenever we have something that's normally distributed, the mean is equal to the median, which is equal to the mode. All three of these are equal to each other. And that's like the center of our spread for our data. Now, as we continue to think about the heights of the people, the students within JTHS, you have very few students who are very, very tall. So therefore, you'd only have a few students within this group. So these are like your 6 feet plus heights. Okay, but again, think about it. You have very, very students, a very small amount of students who are very, very short. The majority of your students are of average height. So this is maybe your 5'6", 5'7" or so. And then as you continue to get bigger and bigger, or taller and taller, there's less and less people who are falling within those higher heights. Okay, so the main key to this part is that if you have a data set that is normally distributed, then your mean, your median, and your mode will be exactly the same, and it occurs directly at the top of your normal distribution curve. Here's another example: female shoe sales. So this was a data collection of course, the shoe sizes of females. As you can see, we have the shoe size of a size 4 all the way up to a size 14. Now think about it. The women that you know in your life, some of them have really, really tiny feet. You may or may not know a person who has really, really large feet. But you do know a lot of people whose shoe size is about a size 8. Maybe a woman whose shoe size is about a size 8. This is the average size for a woman, average shoe size for a woman. So in this particular chart, we can see that this information is normally distributed. In other words, there's no bias from the left nor from the right. The majority of our population is all within our middle. So these are again our average shoe sizes. Okay, not very many people wear a size 4 who are women. Not very many women wear a size, in this case, like a 10.5 or higher. Not many women wear that higher shoe size, and not many women wear that lower shoe size. Most of your data is congregated in the middle. So once again, takeaways, it's important to note that at the very, very top of your graph, we have the mean, which is equal to the mode, which is equal to our median. So the average, which is the mean, the most people, which is the mode, and then our median, the middle number, or the middle number within our data set. All right, so one last example. For those of you who like to play games with dice, there's a very, very important reason for why lucky number 7 is so lucky. And so this graph here shows us the probability of rolling a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12 when we have two pair of fair dice. So you'll notice that once again, this data is normally distributed. In other words, there's no bias to the left nor to the right of our graph. If you are to roll a 2, there's one possible way that you can roll a 2. You roll 1 on one die and a 1 on the second die. You roll a 2. Two possible ways that we can roll a 3, and so on and so forth. Notice what's at the top of our graph, or what gives us the most possible outcomes. That's 7. In order to roll a 7, there are 1, 2, 3, 4, 5, 6 ways to roll that 7. It has the highest there's the highest probability that you will roll a 7. And so that's why a lot of people, when they play dice, they're like, come on, lucky number 7. Because 7 is so-called a lucky number. But that just simply means that you have more chances to roll that 7. Okay, so once again, on the left as well as on the right, there are less possible ways that you can roll these higher or lower numbers. And when you get to that 7, this is the most probable in this case that you will roll a 7. Once again, at the height of our normally distributed curve, we have that the mean, the average number, is equal to the mode, the one that appears the most, which is also equal to the median. Okay, if you haven't realized yet, the takeaway of a lot of this lesson will be the simple fact that at the height of your normally distributed curve, you have that the median is equal to the mean, which is equal to the mode. All three are equal to each other. Let's continue. All right, so a few definitions. Normal distribution, first off, is a function that represents the normal distribution of many random variables as a symmetrical graph. Symmetrical meaning that graph has the exact same characteristics on the left as it does on the right. So it is symmetrical. If you think back to your younger years, if we were to fold this graph upon itself through the line of symmetry, then we'd have that this half of the graph directly lines up with this half of the graph. So that's symmetrical. Next we have the sample mean. This is simply the average of a sample. In lessons 1 and 2, we talked about how to compute the mean, which is the same word as average. And that's by adding up all of your data and then dividing by the number of data points within that particular data set. For the sample mean, we use the symbol here, which we call X bar. So this line above it is called X bar. We call this X bar. And we use it to represent the sample mean, so the mean of a sample. And please note the following. Sample mean, whenever we have a set of data that we've collected, if we do not take the data of an entire population, so let's say that we wanted to collect data on the age of every student within JTHS when they lost their very first tooth. We may not get around to every single student to ask them, what age were you when you lost your first tooth? So therefore, what we could do, we can randomly choose people within JTHS to be a representative of everybody within the school. Or we could choose a specific few classes within JTHS from the West Campus and the Central Campus to be our representatives of the entire population. And so we'll call that the sample. They're the sample out of the entire population of students. So this is simply the sample mean. So whenever we're only talking about a specific group of the larger group, that's simply called the sample. So sample mean. Next we have standard deviation. It is a distance of a set of data or a data point from the mean. So let's say that we're looking at the average woman shoe size. We remember, if you can remember, that the highest height was about an 8, size 8 shoe. So if we're looking to figure out the standard deviation, let's say that we're looking, well, from that size 8 shoe, that size 4, which was way over here in our data, in our normally distributed curve, our data, we would want to know, well, how far away is that size 4 from the mean? So that's just an example of how we'll use the standard deviation. All right, so one of the most important things that you will need to know within this unit is called the empirical rule. And you'll need to know how it works. So this is to be highlighted on your notes, the empirical rule. The empirical rule tells us how the data is spread in a normal distribution as long as we know the mean and the standard deviation. So those are two key things that we need to know, the mean and the standard deviation. Within every normally distributed curve that we'll be looking at, there's going to be some very, very similarities for every single one of them. So the very first thing that we talked about was that here we have that the mean is equal to the median, which is equal to the mode. So that's one thing to always represent. In the middle of your normally distributed curve, you have the mean, which is equal to the median, which is equal to the mode. Up here, we learned the symbol for mean. It is this X bar symbol. So instead of writing the word mean, we'll use X bar. X bar is directly in the middle. To the left of the mean, we have one standard deviation away. And I'm going to use 1S because S is our symbol for the sample standard deviation. So this is one standard deviation to the left of our mean. Then we have 2 standard deviations to the left of our mean, and then 3 standard deviations to the left of our mean. If we look on the right-hand side of our mean, this would be 1 standard deviation to the right, 2 standard deviations to the right, and 3 standard deviations to the right. If you want to think about these standard deviations, it's almost like thinking about, well, here's the mean, we're in the middle. This is 1 step to the right, 2 steps to the right, 3 steps to the right. Or 1 step to the left, 2 steps to the left, 3 steps to the left. So if you want to think about it like that, that's fine. But just know that these are 1 standard deviation to the left, 2 standard deviations to the left, and so on and so forth. So that's just the vocabulary to use mathematically. But if it helps you to think about them as steps, perfectly fine. Okay, it's good for you to note that there are always 3 lines drawn on each side of the mean, which is again the same as X bar. So notice that here we have a line 1, 2, 3. So 3 lines. This was our mean. There's 3 on the right, 1, 2, 3, and then there's 3 on the 1, 2, 3 on the left. So 3 lines always. And that stands for our 3 standard deviations to either the left or to the right of our mean. Next thing that happens in all of our curves is that within this section, this represents 34% of our data. This one is mirrored because once again, this is a symmetrical curve. This bell shape is symmetrical. So what we have on the left is going to be mirrored on the right. So 34% of our data is here, 34% of our data is here. So this simply means that 34% of our data had scores maybe that lied between whatever this score range would be and this score. Okay. Next, within this slot, this represents 13.5% of our data. And so mirrored, this is 13.5% of our data as well. Next, in this slot, this would be 2.35%. And I'll write that a little bigger I'll kind of point an arrow in this space from there to there. That is 2.35% of our data. And mirrored on this side would also be 2.35% of our data. Okay, if you added these numbers up, we'd get a number that's very, very close to 100. If I zoom in a little teeny, you'll see that there's a little bit more space, and that space is here. Within this space here, and it is mirrored on the opposite side too, this is about 0.15% of our data. So it's a really, 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 really tiny percentage of our data. And then same thing here. Over here, this is about 0.15% of our data. So please note that all together, and you guys can stop and actually add it up, 0.15 plus 2.35 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15, it should give you 100%. So 100% of our data will be represented under our normal distribution curve. Again, this is 34, 34, and so on and so forth. Once again, mirrored on both sides. Now, we can think about this in a little bit of a different way as well. And this is also what I'd like for you to take note of. In the middle of our normal distribution curve, this together represents 68% of our data. Well, how'd you get 68, Ms. Collins? 34 plus 34 is 68. So 68% of our data lies within one standard deviation of our mean, is what we call this. So that's one standard deviation to the right, as well as one standard deviation to the left. This whole space represents 68%. Okay, and we would again call that one standard deviation. Shorthanded, one standard deviation. If we're at our mean and we go out 2 standard deviations to the left and then 2 standard deviations to the right, then that would represent this space. We call this 2 standard deviations. And that represents 95% of our mean. Okay, well, how do we get 95%? Well, 95%, it comes from adding 13.5 plus the 34 plus the 34 plus your 13.5. So the amount of data within this section, this section, this section, and this section, these 4 sections in the middle, that's 95% of your data. So they're telling you 95% of your participants within your study are within the first 2 deviations of the mean. All right, and then last important number for you to remember is if you're at your mean, and you go out 3 standard deviations to the left and 3 standard deviations to the right, then we have 99.7% of our data. And this is 3 standard deviations. Well, how did you get 99.7? 99.7 came from adding up our 2.35 plus our 13.5% plus our 34% plus our 34% plus our 13.5% plus our other 2.35%. So this here, we would say that this is 3 standard deviations from the mean. It represents 99.7% of your data. So if we took some type of calculations, 99.7 of our respondents were in 3 standard deviations of the mean. Okay, knowing the different parts of this graph are going to be very important for the remainder of the unit. You will see it repeated over and over in many different ways. Please commit it to memory. All right, let's try some actual practice problems, putting all of these definitions to work and seeing exactly what it all means. So example 1, given the mean, which again is x bar, is 64 and the standard deviation, S, is 3. Graph the normal distribution and label the axes. So first off, our important information is that we have the mean. Second piece of important information is we also have our standard deviation, and it's 3. So that mean, remember that it's located directly in the middle of your normal distribution curve. So here, this is 64. The standard deviation is telling you how far apart your data is from your mean within your standard deviations. So 1 standard deviation, this is 3 away from the mean. So if you're thinking about a time, not a timeline, but a number line, in a number line, let's think 3 back from 64. 3 back from 64, 64 minus 3, this would be the number 61. If we go 3 more backwards, so 61 minus another 3, this is 58. And then 58 minus another 3, this is 55. So far we filled in the left-hand side of our normal distribution curve, 61, 58, 55. And now let's fill in the right-hand side. So 64, which is our mean, a standard deviation of 3. So that means 1 standard deviation to the right is 3 more. So 64 plus 3 gives us 67. 67 plus 3 gives us 70. And then 70 plus 3 is 73. And then that's it. So we've entered our mean, which is 64. Then we used our standard deviation, was just 3. Just tells us that each deviation is 3 more or less than our mean. So we had 64, we went back 3, back another 3, and back another 3. When we had 64, to get to the right, we added 3, add 3, add 3 more. Okay, next example. We have our mean, which is 35, and we have our standard deviation, which is 4. The first thing we should place is our our mean, which is 35. Next, using your standard deviation of 4, we're going to go in increments of 4. So if we're going to the right this time, let's start with the right. We'll have 35 plus 4 gives us 39. 39 plus 4 gives us 43. And 43 plus 4 gives us 47. Going backwards, we have 35 minus 4 will give us 31. Minus another 4 will give us 27. And minus another 4 will give us 23. So our normal distribution curve with the labeled axes is as it's shown. A few more examples. We have example number 2. Given an approximately normal distribution with a mean of 120 and a standard deviation of 40, we need to answer the following questions. So first, highlighting the important information. We have a mean of 120. We have a standard deviation of 40. So the first thing we want to do is go ahead and enter that information into our curve. So the mean goes directly in the middle. It's 120. Our standard deviation is 40. So that means that going to the right, we're going to be adding 40. So we'll be at 160. Add another 40. We'll have 200. And add another 40. Oops, add 40. Add 40. We'll be at 240. Okay, we're going the backwards way. We're taking 120 and subtract 40. We'll land at 80. Subtract 40. We'll land at 40. And subtract 40 again. We will land at 0 in this case. So our normal distribution curve, if we label the axes, our numbers remaining are the numbers that we're using. So this is a 200. I kind of got erased. All right. So our very first question asks us, what is the interval that contains 68% of the values? If you were to go backwards in your notes, you should remember the following percentages. We have 34% of our data here, 34% of our data here. Next, we have 13.5%, 13.5%. Again, it's all mirrored. And then here we have 2.35% and 2.35%. Well, remember that within one standard deviation, so one to the left of the mean and one to the right, this is one whole standard deviation. This is 68% of our data. You can check that by adding these two intervals, 68%. So 34 and 34. So the question is, what is the interval that contains 68% of all values? So between what two numbers contains this 68%? Well, those two numbers are your 80 and your 160. Within the 80 and 60, we have our 68%. So our answer for this question is between 80 and 160. Or you can say 80 to 160, either or. The next question asks, what is the interval that contains 95% of all values? If we were to go back to our notes, you should recall that 95% of your values falls within two standard deviations of the mean. So that means if we're at the mean and go two standard deviations to the left, 1, 2, and two standard deviations to the right of our mean, 1, 2, then that means that this space in between these two numbers is two standard deviations, which is also known as 95%. Visually, that means that we've added these percentages up: 13.5%, 34%, 34%, and 13.5. So that's 95% of our data. To answer our question, they said, what is that interval? So that's between our 40 and our 200. So our answer is 40 to 200. All right. The last part, part C. What is the interval that contains 99.7% of all values? 99.7% is 3 standard deviations from the mean. So if you're at your mean, we go 3 to the left, 1, 2, 3. We're here. And 3 to the right from the mean, we are 1, 2, 3. We're here. Then we're talking about this interval. So this is 3 standard deviations. It's also known as 99.7% of our data. Visually, it's from here, 2.35% plus 13.5% plus 34 plus 34 plus 13.5 plus the 2.35. So that's 99.7% of our data. So it says, what is the interval? Then that interval is between 0 and 240. So 0 to 240. Example number 3. The test scores of a math placement exam have an approximately normal distribution with a mean score of 520. That's important. Mean of 520. And a standard deviation of 40. So our second important piece of information. Let's go ahead and draw in our normal distribution curve. In the middle, we'd have our mean, which is 520, and our standard deviation of 40. So that means that we're going to be adding and subtracting our 40s. So to the right, we'll add 40. We'll land at 560. Add 40 again. So add 40. We'll be at 600. And then add 40 again. And we'll land at 640. Going to the left, we are subtracting 40. So therefore, we are at 480. Subtract 40. We're at 440. And subtract 40 again. We land at 400. Okay, just erasing those adding and subtract marks. Don't need too much information down there to confuse us. So 560 is there. All right, so we've drawn in our normal distribution curve. Once again, in the middle, we have our mean. And then we use the standard deviation to come up with each of our other intervals. Our first question is, what percentage of students who take the exam score between 480 and 560? So let's highlight those two. So 480 is here and 560 is here. They're asking us what percentage of students who take the exam score between 480 and 560. So what percentage? Well, using the empirical rule for our normally distributed curve, we know that 34% of our data is within the first standard deviation of our mean. So 34 and 34. 68% of our data. 34 over to the left of our mean and 34 to the right. And notice that the interval 480 to 560 is within one standard deviation of our mean. So if we were to take both of these intervals here and just go ahead and add them up, we'd get 68%. So our answer is 68%. Okay. All right, part B. What percentage of students who take the exam score between 520 and 600? So keywords, they're asking again, what percentage? And they're asking are between 520 and 600. So 520 is our mean and 600 is located here, 2 standard deviations to the right of our mean. So in order to answer our question, let's highlight these two intervals. So between 520 all the way to our 600. Notice the two intervals that are highlighted, the 34% and our 13.5%. In order to figure out our answer, we simply add the two. So 34 plus 13.5 is equal to 47.5%. And that's our answer. All right, so starting off again from scratch with our problem for part C. What percentage of students who take the exam score between 400 and 440? So highlighting the important parts, we again are asked what percentage, and this time are between 400 and 440. 400 is located here and 440 is here. Each of these, if we were to highlight the interval between 400 and 440, we'd only highlight this little slither right there. Okay, And notice that the empirical rule already gives us what that percentage is for this interval. It's 2.35. So in this case, our answer is 2.35%. And we are finished with part C. All right, example 4. We have a company packages sugar in 1,000 gram bags. When you weigh a sample of the bags, you find that the sample mean is 1,010 grams and the standard deviation is 20 grams. Then we're asked 3 questions. So let's start off like we have done in the past. We start off with our sample mean, and they've told us that our sample mean is 1,010 grams. And then as well as our standard deviation is 20 grams. So let's use those 2 pieces of information and write them into our normal distribution curve. So our mean is 1,010. 1010 is our mean. Our standard deviation is 20. So that means we're going to add 20 going right to each interval and subtract 20s going towards the left. So 1,010 plus 20 will give us 1,000. This is 30. Then we'll have 1,050 and then 1,070. Going backwards, we'll have 990. We've subtracted 20. Subtract another 20. This is 970. And subtracting another 20, this is 950. Okay. All right. For this problem, since again, each of our little questions here are asking us about what percentage, and what percentage, let's go ahead and write in our percentages for our normal distribution curve based on the empirical rule. So here we'll have that this is 34%, 34%. Notice how the numbers are still the same as the very first time you were introduced to them. 13.5%. This one is 2.35% and 2.35%. Okay. All right. Now let's go ahead and answer our questions. Part A, what percentage of the data falls between 970 and 1050? So 970 and 1050. 970 and 1050. So 970 is here. And we have 1050, which is located here. If we are to go ahead and highlight the intervals in between, we'd have from 970, we are going all the way to 1050. And let's add these up together. 13.5% plus our 34% plus our 34% plus 13.5% is going to give us 95%. So our answer for part A is 95%. Okay, and once again, you can either add up your 4 intervals or note that that's 2 standard deviations of the mean, which is 95%. All right, part B. What percentage of the data falls between 990 grams and 1,070 grams? 990 grams is located here. 990. And 1070 is here. If we're looking to figure out what percentage of the data falls between those intervals, once again, we can go ahead and highlight them. So from 990 all the way to our 1070. We have to add the numbers between these 4 intervals. So 34 plus 34 plus 13.5 plus 2.35. So once again, that's 34 plus 34 plus 13.5 plus 2.35. And it's equal to 83.85%. And that's our answer. All right, and our very last question. What percentage of the data falls between 990 grams and 1050 grams? 990 grams is located here, and 1050 of the grams are located here. If we highlight that particular interval, we have 34%, another 34%, and 13.5%. Okay, so then if we were to go ahead and add 34% plus 34% plus 13.5%, we'd end up with 81.5%, which is our answer for this problem. Okay, make sure that if you had any questions throughout this lesson, you ask. Thank you.